Welcome back to Skunky Designs, and today we're going to talk about not a specific amplifier or project, but about output transformer impedance. I know that's a real voodoo topic. Ooh, everybody gets all confused about it. It is a pretty confusing topic if you don't really understand what's going on. The confusing part of it is the measurement of resistance and impedance is both in ohms, but they are two different things. And like we have our little meter here that we all know and love that measures in ohms, and we can measure DC resistance or DCR with this meter. And you'd think, well, why can't I just measure the leads or across the terminals of my transformer and with my trusty little meter and get the resistance? Well, you can, but that's the DCR of the transformer, which has nothing to do with the impedance. On a tube amplifier, it uses reflected impedance through the transformer. And what that means is the load that you put on the output is reflected through the transformer based on the turns ratio, and that's what the tube sees. And so you can figure out what the impedance of an unknown transformer is by measuring the turns ratio and then doing the math to calculate up what the reflected impedance is. And that's what we're going to be doing today. First, we're going to test a known little musical power supplies output transformer that I have that has multiple taps, so we can hook it up different ways and measure and do the math, and we know what the impedance is supposed to be on each of the pairs of leads. And so we can check our math, make sure we're doing this all right, and I can kind of show you how to measure these things. And then we're going to measure some unknown transformers, which are the output transformers on this Bogey Range A50, because it'd be nice to know what the impedance of these output transformers is as we're doing the measurements and figuring out like what may be different between this and my DIY amp. And it could be the output transformers or what's going to be the difference. So I'm going to get my old trusty Tektronix 2235 oscilloscope hooked up and going to use my TEMA audio generator. I know there's different ways of doing this on the internet. People show using voltmeters and stuff. I'm going to show you how I do it using my signal generator and my oscilloscope, because the other thing to note is transformers only work on alternating current. They don't work on DC. And we also know that these transformers really need to shine in the audio spectrum. So instead of putting like 60 hertz AC through it, I'm going to be putting our old friend 1 kilohertz through it to do these measurements. So the other thing that I want to explain real quick before we get on the scope is how to understand the difference between resistance and impedance. And this may not be perfectly technically correct, but to me this is a way that I can keep it straight in my mind, and I think it's a simple way of understanding it. If we think about resistance, is the resistance to DC that we measure using a handheld meter. And while AC will see that too, if you try to think about it as resistance is the DC resistance. Okay? The impedance is how much the device impedes AC going through it. And so if you can separate that in our mind that DC is resistance and AC is impeded, that'll help you remember that what impedance is doing versus what resistance is doing. Because like as we'll see, this transformer can have very low or really low DC resistance and at the same time have very high AC impedance. And then the other thing to remember is once we get outside the 60 hertz power supply, all the AC that we're seeing inside an amplifier is the music. And that may be a simpler way to think about it too, is that even when we're seeing this 1 hertz or 1 kilohertz sine wave being sent through these amplifiers, that's simulating the music. And so what we're really doing is we're amplifying the music, which is fluctuating voltages that's alternating current. And so maybe that'll help you understand too when we're talking about coupling capacitors, how coupling capacitors let the AC through but block the DC. That really, another way to think about it is it lets the music through while it blocks the DC. So that might help kind of get straight in your mind, because I think once you kind of understand the basics of this stuff, all of this becomes so much less complicated. So that's what we're trying to do today with these output transformers. I'm fixing to crank this thing up on a scope. There's a little bit of math involved, but trust me, it's really easy. We're squaring one number and then multiplying it times another. So this isn't rocket science math either. So let's jump on the scope and do some testing, and I'll show you how all this works. Okay, first we want to set up our scope with channel 1 is going to the output of our signal generator, and it's set on 1 volt. And then the channel 2 is hooked up to what would be the primary of the output transformer. And what we're going to do here is we're going to insert a 1 volt peak-to-peak signal into the secondary of the output transformer, and then we're going to measure the peak-to-peak voltage that we see on the primary. And then because we're doing 1 volt, however many volts we see on the primary is going to be the turns ratio of the output transformer. And also make sure that your signal generator is capable of injecting a signal into this low ohms device. Some signal generators aren't able to, and I'm sure there's some ways to work around it, but this is the way that my signal generator seems to have no problem injecting a signal into an 8 ohm load. So let me show you what we've got here. And we have the signal generator hooked up to the 8 ohm taps on the secondary. And then we have the scope probe leads hooked up to the 7K primary leads on the transformer under test. So here comes 1 volt of signal. You want to try to get this as accurate as you can. It actually might be, let's go ahead and put this on a 0.5 volt and get a little higher resolution. Okay, that's 1 volt in, and then if we count, these are 5 volts per division on the other scan. We got 5, 10, 15, 20, 25, almost 30 volts. I'd say maybe 29 volts on the secondary. Okay, so now we're going to switch to the 5K tap on the primary. and we're going to inject the same 1 volt signal in. It's 1 volt in. We got 5, 10, 15, 20, 25 volts or 25 turns out. So on the 5K, we had 25 turns to 1 ratio. And then on the 7K, we had 29 to 1 winding ratio. And that's what's important, because I'll show you here in a minute when we sit down to do the math on all of these different scenarios, how this plays out. So the next thing we want to do is we want to hook up the signal generator to the 8 ohm taps on this Bowyer range amp that we have no idea what these output transformers are. And I hope it's obvious, but you know, take all the tubes out of the amp, obviously don't have it plugged in, but I think taking all the tubes out of the amp is a good idea too, because we're just testing the transformers. So you put one of the leads onto the plate of the output tube, and the other one's going to be hooked up to the B+, which, if you look at it, we're going to hook right up to the 2 wires going to the output transformer. One of them goes to the plate, one of them goes to the B+. So now we're going to put in a voltage signal again, and we're getting 5, 10, 15, 20 volts at 20 turns to 1 ratio is what these output transformers are on this Bowyer range amp. The other thing I want to show you is what happens when we connect the same 1 volt up to the 4 ohm taps on this output transformer. So we put our 1 volt in, then this time we get 5, 10, 15, 20, 25, 27 turns to 1 ratio. This was one of the things that might seem a little confusing, because you would think that, okay, if we're cutting the speaker load in half, we would cut the turns ratio in half. But that's not how it works. Because if that was how it worked, then it would be 40 to 1 on the 4 ohm and 20 to 1 on the 8 ohm. But as you'll see when we do the math, that's not how it works. And I'll also show you how you can use these 4 ohm taps to potentially make this amplifier perform better. So now we're going to do the math, and I'll show you how you calculate up the actual impedance that's reflected to the tube from the output, which is your speaker load. Okay, so here's our rule here that we need to follow while we're doing this. And I think as you watch me do this, you will see that this really isn't that complicated. So the impedance ratio is the square of the turns ratio. So if we have a 20 to 1 turns ratio, we have a 400 to 1 impedance ratio. What that means, especially if we put in 1 volt and get the turns ratio to 1, which we've done, all you have to do at that point is you multiply the turns ratio times the turns ratio, and then you multiply that times the output load, and that tells you what the primary impedance load that the tube will see is, which is what we're really concerned with. So let's go through a couple of examples. We know that we were measuring a 5,000 ohm primary load transformer into an 8 ohm load, and we got a 25 to 1 turns ratio. So if we multiply 25 times 25 times 8, we get 5,000 ohms impedance, which is what we know this transformer is supposed to be. So The next thing we did was we measured it at the 7,000 ohm tap of the primary. And we got a little over 29 volts. So let's say 29.5 times 29.5. And again, we were using the 8 ohm output tap and 6962. That's very close to 7,000 ohms. This is showing us we measured a known good transformer and we got the right measurements and the right math both times. So now let's do this unknown transformer, which is in the Bowie range A50. And we found, so we go 20 times 20 times 8 ohms, 3.2K primary output transformer, which is actually a little on the low side for a 300B. In that range will also increase the distortion a little bit. I think they probably went with that low K output transformer trying to boost the power, which if you're trying to get power versus THD, it becomes a balancing act. I picked a 5K transformer for my 300B, even though it's a little higher than what a 300B is capable of loading. It normally makes for a lower distortion amplifier, which we saw the figures on that amplifier. The distortion was really low up to where the point it started clipping. So we may not be able to get the distortion numbers quite as low on this amplifier, but we do have the option of looking at how we might be able to use the 4 ohm taps on this transformer. Okay, so if we do the math on our 4 ohm tap, which looking at it more closely off camera, it was right at 28 volts using the 4 ohm tap. So we had a 28-to-1 turn ratio on the 4 ohm tap. And that gets us 3136, which is close to what we were seeing on the 8 ohm tap as far as the reflected load. But what I want to see is if we multiply this times a 6 ohm load, which is what a lot of 8 ohm speakers actually come out to be, we're real close to a 5K load on the output tube. So what this is showing me is look at your speakers and see if you can find reviews on them to look at their impedance curves. And if the speaker is really closer to a 6 ohm load rather than an 8 ohm load, you probably want to be hooking it up to the 4 ohm taps. Or if nothing else, it's worth at least trying that and seeing how the amplifier sounds. If you don't need the power that hooking your speakers up to the 8 ohm tap gives you, hooking up to the 4 ohm tap will likely give you less distortion at all listening levels. So the last thing I want to do is see what happens if we just hook a plain 8 ohm speaker up to the 4 ohm taps. See, that's getting up there a little high. That's, over 6K. But again, it may sound better. So it's well worth trying hooking your speakers up to the 4 ohm taps instead of the 8 ohm taps. But again, as we get more into working with this Bowie range amp and seeing what the distortion numbers are like, we'll know more. But this is some pretty simple math. You're multiplying 3 numbers together. And once you figure out the turns ratio, you can start calculating up the different scenarios and hooking the amps up to different taps and exactly what you're working with. So to wrap up this video, as you can see, this isn't really complex math. I mean, some of these guys I see doing math stuff with tube amplifiers, There's just pages and pages and pages of stuff. This is really simple. We're multiplying three numbers together. And there are all kinds of ways of generating 1 volt of AC and then measuring it. I'm sure you can do it with one of these. I just happen to use my signal generator, my scope, because it's sitting here on my bench. But I've seen other people using just these digital multimeters. So all you need is a 1 volt AC signal to inject into the output of the transformer to figure out the turns ratio. Then once you figure that out, you can do this simple square the turns ratio multiplied by the load, and you get the impedance that is going to be seen by the output tube, which is what really is one of the most important things with getting an amplifier to work right. The other thing this doesn't tell you is how many milliamps of current that the transformer can deal with and how many watts of power that the amp can make using this transformer. And you can get a pretty good judge of the wattage that the transformer can deal with by the size of the transformer. Like, this is a little guy here, 8 watts. You got one that's, that small, it's probably 8 to 10 watt maximum. A little bit bigger, obviously, is 15 to 20 watts. So there's not a lot of tubes that would put out more than that on an SE amp anyway. And only things like the KT88 and like a 300B are going to draw the milliamps where that would be really a concern anyway. So anyway, just acknowledging that while you know the turns ratio, you still don't know how many milliamps that it will be able to handle and how many watts it can put out before it gets saturated and goes into distortion. But again, the size of the transformer will give you a good clue as to, what kind of power level that transformer can handle. I really hope this helped clear up some of this confusion. I know at first I was really confused about this, but once I kind of understood the turns ratio and the difference between resistance and impedance and when they're used, it really helped me get a grasp on what's going on tube amplifier output transformers. So, hope you enjoyed this video. If you enjoy the channel, please sub, like the video, and I'll see you soon for more tube amplifier fun. Have a great day.